The lecture for section 3 of chapter 1 in the book Problem Solving with Differential and Integral Calculus is split into two parts. We're going to tackle something new here. The first part of the lecture deals with the difference equation, and the second part deals with the slope of the line. The equation for the area of a square is A is s squared. That's the normal equation. If we have a square with side length s, the area is s squared. For example, if a side length is 4 feet, we can draw a grid. In the lower left, we have a 1 foot by 1 foot square that has an area of 1 square foot, and there are 16 of those. Unlike the circumference and the perimeter relationships, which we dealt with in sections 1 and 2, this relationship is not linear. Perimeter is 4s, that's linear. Circumference 2 pi r, that's linear. The area of s squared, that's going to be a parabola. It's an exponential relationship. There it is. We can plug in different side lengths and get different areas. If you double the side length, for example, from 5 centimeters to 10 centimeters, going from 5 to 10, the area goes from 25 to 100 square centimeters. The area is quadrupled. Similarly, if you go from a side length of 2 centimeters to 8 centimeters, which is a factor of 4, the area goes up by a factor of 16. We have a 4 square centimeters here, and we have 64 square centimeters here. So now we're going to shift gears and look at the differences. This is all normal equation right here. What are the differences? What's the difference equation that gives delta A, the difference in the area between two squares based on the difference in their side length? So here's a square with side length s. Here's a different square with side length s plus delta s. The area of the top square is just the side length squared. The area of the bottom square is also its side length squared. But in this case, the side length is s plus delta s. If we subtract those two areas, we get delta A. So the difference is s plus delta s quantity squared minus s squared. If we multiply out that first term on the right-hand side, we get this, and we have an s squared here, and we have minus s squared here, and here is the difference, 2s delta s plus delta s squared. And we should think about why that's delta A. Why is this true? And a picture will tell the story. So the square in white is just an s by s square, and the total square is s plus delta s, the outer square. The difference in their areas is the grayed in portion. These are rectangles. This one is s by delta s. This one is s by delta s. That's the 2s delta s, and here we have the delta s squared, and that is delta A, which is why delta A is 2s delta s plus delta s squared. It's not magic. It's not something to accept. It's a concept to understand. So let's do a specific example with numbers. We're going to deal with square with a side length of 5, and we're going to increase it by 3 centimeters, up to 8 centimeters, and we're going to get the difference in the area. So there's the delta S, and here is the delta A. And we can just plug in the numbers, subtract the areas, we get a delta A of 39 square centimeters. Now we're going to use the difference equation to get that same number. So S is 5 centimeters, delta S is 3 centimeters. 2S delta S, that's 30 square centimeters. 3 centimeters squared is 9 square centimeters, so we get our delta A as expected. And we can look at a picture. There's 5 by 5, there's 25 squares there. This rectangle is 3 by 5, which is 15 square centimeters. Here's another 3 by 5 rectangle. That gets us up to 30, and this square is 3 by 3, which is 9 square centimeters. That's how we get delta A. In the next lecture, we're going to deal with the slope of the line, and it's curved. How do you get the slope of a curved line? Watch section 2 and find out.